Hello friends, this is Lalit Vasist and you are watching Engineering Made Easy. In today's video lecture, we are going to discuss all the four Maxwell equations. These are very important equations and we will see the derivation of all these four equations. So here you can see these are the four equations of Maxwell in differential form and integral form. Here you see this is the differential form, four equations, and this is the integral form of these equations, and this is the significance. So before starting the derivation, let me show you these four equations. The first equation is curl of E is minus del B by del T. You see here these two equations are in curl and two are the divergence equations. You should know the basics of curl and what is meant by the divergence. So this is the differential form. The first equation is curl of E is equals to minus of del B by del T, and its integral form is given as this. I will explain you what does this all mean with derivation, and this is based on the Faraday's law of electromagnetic induction. Okay. The second equation of Maxwell is curl of H equals to J plus del D by del T, and this is based on the Ampere's circuital law. This is its integral form. You can read all these. I am not explaining it at this point. I will explain you later in this lecture, so keep watching it till the end. Divergence of D is equals to rho V, and divergence of B equals to 0. So divergence of D is equals to rho V is based on the Gauss law, and divergence of B is equals to 0 is based on no isolated magnetic charge or monopole exist. I will explain you what this mean because we will see all of them one by one. So don't worry. Let's start with the first Maxwell's equation, curl of E equals to minus of del B by del T. Let's see its proof. So our first equation is this, curl of E equals to minus of del B by del T. How we can prove this equation? It is very easy because as I told you, it is based on Faraday's law, and we know what is Faraday's law. According to Faraday's law, the induced EMF, okay, is equals to minus of d phi by dt. Phi is the flux, so it means that the EMF induced is equal to the rate of change of flux. Let's say we have a loop, okay, and a bar magnet, okay, and if I move this bar magnet inside and outwards of it, so it has, since we know it has magnetic lines of forces, and these magnetic lines of forces emit from the north pole and enter into the south pole. When I move this magnet inside and outward of it, then there is a change in the flux inside this loop, and because of this EMF is induced in this loop. So according to this induced EMF equals to minus of d phi by dt, the rate of change of flux. More will be the change in flux, more will be the induced EMF. So we can write this potential as integral E dot dl, okay, by formula. Integral E dot dl is the voltage, and this flux is equals to integral of B dot ds, okay. So d by dt of integral B dot ds. You should know these very basic formulas, okay, and we can again write it as integral E dot dl equals to minus of del B by del T. We can write it as, take this derivative inside this integral, and it becomes minus of integral del B by del T. This is partial derivative, okay, dot ds. Now by the Stokes theorem, actually what is the Stokes theorem? According to Stokes theorem, we can change the line integral into the surface integral. So we can change this integral E dot dl into curl of E dot ds. Here it is in line integral, it is the line integral, and when we take its curl, it converts into the surface integral. So this is very important theorem known as a Stokes theorem. So we have changed this integral E dot dl into curl of E dot ds, and by this curl of E, at the place of integral E dot dl, I am writing curl of E dot ds, which is equals to minus integral del B by del T. This is a surface integral, okay, this is the surface integral. Now by comparing both of these sides, look at this, since these both are equal and both are the surface integrals, so by comparison you can easily understand that curl of E is equals to minus of del V by del T. So this is what I wanted to prove, that curl of E equals to minus of del V by del T. This is the Maxwell's equation, first equation you can say. So this was the proof. It is based on the Faraday's law. Now this is the second Maxwell's equation. Divergence of D equals to rho V. So here D is the electric flux density and rho V is the volume charge density. Now let's prove this. Actually this is based on the Gauss law. According to Gauss's theorem, the total electric flux that is passing through a closed surface is equal to 1 upon epsilon times the total charge enclosed within the surface. Okay, it is clear, very clear. The definition is very simple and clear. So mathematically we can write it as surface integral d dot ds is equal to the charge enclosed. It means this surface integral is the flux, and this flux integral d dot ds denotes the flux, which is equal to the charge enclosed within that enclosed surface, within that imaginary enclosed surface. We can write it as, since d equals to epsilon naught times of electric field intensity, E is the electric field intensity and d is the electric flux density. Since d equals to epsilon naught times of E, we can write integral d dot ds as E dot ds equals to q by epsilon. This is q is same, q enclosed. Okay, so this is the Gauss theorem. Now since we know that this rho v is the volume charge density, and because of this we can write the charge q is equals to the volume integral of rho v dv. Okay, if we integrate this volume charge density with respect to volume, the volume integral, then I will get the charge q. So at the place of charge q, okay, this charge q enclosed, I can write the volume integral of v dv. Okay, so let's write it. Okay, surface integral d dot ds, the flux is equals to the charge q enclosed. Okay, rho v dv. Now by the divergence theorem, we have seen the Stokes theorem earlier in the first Maxwell's equations proof. Now we will see the divergence theorem. It is also known as the Gauss divergence theorem. Since the Stokes theorem shows the relationship between the line integral and surface integral, this is based on the relationship between the surface integral and the volume integral. Okay, so integral d dot ds, it converts this surface integral into the volume integral. So d dot ds can be written as divergence of d dv. So this surface integral has been changed to the volume integral if we take the divergence of this vector field, the electric flux density. Now at the place of integral d dot ds, I am writing the volume integral divergence of d dv, and this is as it is. Okay, I've changed this equation into this one, and from this, by comparison, you can easily understand both are the volume integrals. Since these are equal, we can write that divergence of d is equals to rho v. This is what we wanted to prove, and this one is a second Maxwell's equation based on the Gauss law. We proved it by using Gauss law. Now let's come to the third Maxwell's equation. The third Maxwell's equation is the divergence of B is equal to 0. This is again an important equation. So how we can derive it? Actually, it is based on the postulates of magnetostatics, which states that there are no magnetic flux sources and the magnetic lines always close upon themselves. And it says that no monopoles exist. Since the magnetic lines of forces form closed paths, they start or they emit from the north pole, reaches to the south pole, okay, outside this magnet, and inside this magnet it moves from south to north. So the direction of arrow is in this way. So it is forming a closed path. Okay, in the same way, let's see this one also, starting from the north pole going into the south pole, okay, in this way, and inside this it is following the same path, that is closed path. So because of this, we can say that they do not have any, there are no magnetic flux sources, and these magnetic lines always close upon themselves. Okay, they form closed loop. This is the law of conservation of magnetic flux. Okay, it also means that the number of magnetic lines that are entering into a surface is equal to the number of lines leaving that surface. Okay, because of this, we can write that integral b dot ds is equals to 0. That is, the flux equals to 0. The number of magnetic lines entering into a surface is equal to number of lines leaving that surface. So we can say that integral b dot ds is equal to 0. So what is integral b dot ds? It is the flux. So flux is equal to 0. The magnetic flux equal to 0. So integral b dot ds is 0. Now see, we have seen the Gauss divergence theorem. Let's see it again. So by the Gauss divergence theorem, we know we can convert this surface integral into the volume integral. So from this integral, the surface integral b dot ds can be converted into the volume integral by taking the divergence of this magnetic flux density. B is the magnetic flux density and H is the magnetic field intensity. Okay, so understand the difference, and this B is equals to mu naught into H. You should know the relationship. So we have changed this into this one. Now since this was equal to 0 and we have converted it into this one, this form, using Gauss divergence theorem, so this quantity is equal to 0. So we can say that if the volume integral of this is 0, then it must also be 0. So divergence of B must also be 0. So from the integral B dot ds equal to 0, we can derive, using Gauss divergence theorem, that divergence of B equal to 0. Okay, this is the third equation of Maxwell. Okay, now we will see the fourth and the final equation of Maxwell, which is based on the Ampere's circuital law. The fourth equation is curl of H is equals to J plus del D by del T. Here, as I told you, H is the magnetic field intensity, J is the current density, and what is D? D is the electric flux density. Okay, so this curl of H is equals to the summation of J plus del D by del T. Now we will prove this with the help of Ampere's circuital law. Okay, since we know that by the Ampere circuital law that integral, the line integral, this is line integral, integral B dot dl is equal to mu naught into I, and we also know that this B is equals to mu naught into H. So we can replace this B by mu naught into H in this Ampere's circuital law. Magnetic, this is a magnetic flux density, and this is magnetic field intensity. So from this we can write H is equals to B by mu naught. Now B is equals to mu naught into H. So from this we can write B by mu naught equals to H. So if I transfer this mu naught to this side, so B by mu naught, okay, is equal to I. So B by mu naught is H. So I can write integral H dot dl equals to I from this relationship. Now this is again the Ampere circuital law in the form of H. Now I also know that current I is equals to surface integral J dot ds, because J is nothing but the current density. J is equals to I by A. So if I take the surface integral of this current density, then I will get the current I. So at the place of I will write surface integral J dot ds. So this equation converts into integral H dot dl equals to surface integral J dot ds, line integral and surface integral. Initially we have seen that we can convert this line integral into the surface integral using the Stokes theorem. So I will use the Stokes theorem to convert this H dot dl, that is this line integral, into the surface integral and replace it by that surface integral. So integral H dot dl can be written as, using the Stokes theorem, as this: integral H dot dl equals to curl of H ds. Okay, this is surface integral, line integral converted into surface integral using Stokes theorem if we take the curl of this vector field. So just replace this by this, and it was on the right side in the previous expression. Okay, so integral j dot ds. Now on both sides I have ds, and by comparison I can see that since these both are equal, so curl of h must also be equal to j. Okay, both are surface integrals and these are equal, so we can write curl of h equals to j. Now you see that our equation was not this one. Our fourth equation of Maxwell was curl of h equals to j plus del d by del t. See here that our original equation was curl of h equals to j plus del d by del t, but we have derived this part only, curl of h equals to j. So what about this del d by del t? So this equation curl of h equals to j is valid only for the steady magnetic field. This is the Ampere circuital law, and which applies to the steady magnetic field, that is not varying magnetic field. But I need to modify it if I want to use it for the time varying conditions. And for time varying conditions, if I want to, then let's see what happens if I take the divergence on both sides of this equation. So curl of h, so take divergence on this side, so it becomes divergence of curl of h equals to divergence of j. Okay, on both sides, since this divergence of curl of h equals to 0. Why it is 0? Because this is the cross product and here is the dot product. These are the same vectors. Okay, so we know that if we cross product two vectors, then the resultant will be perpendicular to both of these vectors. So it means that the resultant vector is perpendicular to this and this both vectors. Since the resultant vector is perpendicular to this vector and this is the same vector, so it means the resultant vector is perpendicular to this vector, and if we dot product two perpendicular vectors, then we get the resultant as 0, because the dot product is equals to, if two vectors are there, a vector and b vector, and they are perpendicular, so it will be magnitude of a into magnitude of b into the cos of theta, where theta is the angle between these two vectors, and cos 90 is equals to 0. Okay, cos theta is 90, then it will be 0. So it means that divergence of j is 0. So now we have seen that divergence of j is 0, but there is a problem with this, because according to the equation of continuity, the divergence of j plus del rho v by del t is equal to 0. J is the current density, rho v is the volume charge density. So from this, divergence of j is equals to minus of del rho v by del t. But we have seen that divergence of j equals to 0 in the previous expressions. So it means that del rho v by del t should be equal to 0. But being del rho v by del t equal to 0 is an unrealistic limitation. Okay, that del rho v by del t should be equal to 0 is the unrealistic limitation. So we must make changes to the equation of curl of h equals to j to use it for the time varying fields. So as we have derived earlier that curl of h is equal to j, but on solving this, it is not complying with the continuity equation. For this, it is the condition that del rho v by del t must be equal to 0, which is unrealistic limitation. So there must be some another term. We should add another term to this j, so that we can use it with the continuity equation. Okay, so for this we will add another term, let's say g term. So we will write curl of h equals to j plus g. Here g is any unknown term. Okay, so our equation is g, our equation is curl of h equal to j plus g, and I want to find what is the value of g, and then I will replace it. Then it will be valid for the time varying fields also. Okay, and we can use it with the continuity equation. It will not contradict. Then let's take the divergence on both sides. So divergence of curl of h is equals to divergence of j plus divergence of g. I have seen that divergence of curl of h is 0. Okay, the reason I have explained you, this is dot product, this is cross product, so it is 0, and from this divergence of j plus divergence of g is equal to 0. From this I got divergence of G is equals to minus of divergence of J. Okay, transfer this to this side, and I also know by the equation of continuity that negative of divergence of J is equal to del rho V by del T. We have seen that by the equation of continuity, divergence of J is equal to minus of del rho V by del T. So I can write it as negative of or minus of divergence of J is equal to del rho V by del T. So here is the same thing. Minus of divergence of J equals to del rho V by del T by the equation of continuity. So I got this. This is equal to divergence of G. I also know that divergence of D equals to rho V. We have seen this is a Maxwell equation, that divergence of the electric flux density is equal to the volume charge density. This is a Maxwell's equation. So by using this Maxwell's equation, I can replace the rho V by the divergence of D. So at the place of this, I will replace it by divergence of D. So I got divergence of G is equal to del by del T of divergence of D. Okay, using this one. Okay, so divergence of G is equals to del by del T of divergence of D. I can write this in the next step. It is equal to divergence of del D by del T. Okay, take this divergence at this place. Divergence of del D by del T. Look here, divergence of G is equal to divergence of del D by del T. Okay, so from this, if you compare these, since these two are equal, and this is the divergence of this, and here is the divergence of this term, so for these to be equal, this has to be equal. The G is equal to del D by del T. So this is a modified form of the Ampere's circuital law for the time varying fields. This is the equation after modification. It can be used for the time varying fields. Up to this point, curl of H equal to J, it was for the non time varying fields. Okay, but here we had the term curl of H equal to J plus G, and G is replaced by this term. We have calculated del D by del T. Now it is the complete Ampere circuital law, or complete Maxwell's fourth equation, that curl of H is equals to J plus del D by del T. Okay, now we can write it as J. This is the actually this form, this J is the conduction current density. Actually both of these are current densities. This is the conduction current density, while del D by del T denoted as JD. D is for the displacement current density. D is displacement, so JD is the displacement current density. So it is a summation of two types of current densities: conduction current density and the displacement current density. So this is a proof of the fourth equation, the Maxwell's fourth equation. So we have seen the proof of all these four Maxwell's equations, and based on these Faraday's, Ampere's, Gauss, and no isolated magnetic charge or monopole. These are based on these phenomena, and this was the differential form and the integral form. If you know how I got these integral, actually we have used these all integral. If you will see the derivation of each of these, you will find we have used all these integral forms also while deriving these equations. We can derive these integral forms directly by integrating them on both sides. Okay, while we use using the Stokes theorem and the Gauss divergence theorems, you can prove them, and you can see the derivation, how we got these integral forms while deriving these. So I should not repeat this lecture to derive these equations. This was for the introduction that I used these both forms, and we have derived them. You can see the video. So I hope you understood all these concepts and how we can derive these Maxwell's equations using these laws. Okay, so did you enjoy this video? For more such videos, you can subscribe my channel Engineering Made Easy, and so that you can get the notifications of my videos as soon as I release them. So friends, thank you for watching this video till the end. See you soon in the next video. Take care. Bye bye. Friends, for more such videos, you can subscribe my channel Engineering Made Easy. And please don't forget to like and share the video if you liked it. For more detailed information, you can visit my blog. See you soon in the next video. Till then, bye bye.